Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to expand your mathematical bag of tricks, and we're going to talk about hyperbolic functions, which is a section that's going to be in your calculus textbook that talk about these hyperbolic functions. And of course, since you're studying calculus, you're not only going to learn about the functions, you're going to learn about their derivatives, okay? So the rates of change of these functions, how to take derivatives of hyperbolic functions. So the first thing you might ask yourself is, what is a hyperbolic function and why do I care? Well, there's, I guess the easiest way to answer that question is I'm of two minds about it. It's important that you know what a hyperbolic function is and to know that they exist and to know what they look like, because you'll find them cropping up in engineering and in your study of physics. They'll come up, sometimes you'll talk about a system and it'll end up reducing down to a sine or a cosine, and that'll be sort of the way the system behaves. Sometimes in some systems, you'll see a hyperbolic fall out of the solution. So one thing that I really wanted to tell you is that these hyperbolic functions, you'll see them in your book. There's a hyperbolic sine and a hyperbolic cosine and a hyperbolic tangent and a hyperbolic cotangent and all of the those analogous terms to your regular trigonometric functions. So for instance, the hyperbolic sine would be written not as a sin like a sine function, but it'll say sin h. The h means a hyperbolic. So why are they named this way? Well, one thing I want to point out to you that you may or may not actually know is the sine function. I'm just giving you a little motivation here more than anything else. Sine of some angle theta. Okay, you've been talking about this all through trigonometry and through calculus, and you know what this means. This is the projection of an angle. When you draw a unit circle, it's the projection of that unit circle radius onto the y-axis. That's what sine of theta means. Okay, but it turns out when you study more advanced math, the sine of an angle is written like this. It's written as e to the I theta minus e to the minus I theta over 2I. Okay, this thing right here is the true form of the sine function. Okay, so you can see that. And by the way, ask me what this is visually, and I couldn't tell you. Okay, this is a complex exponential. You've got e, which is the same e that you always know, raised to I, which is an imaginary number, times theta that you have here, minus e to the minus I theta over 2I. The only reason I even bring it to you here, you'll study this in advanced math. This is what the sine function actually is if you were to write it down mathematically. The reason I say it is because the hyperbolic sine h of some number x is very, very similar, and that's why they call it hyperbolic sine. It's written as e to the x minus e to the minus x over 2. Okay, so you see that right there? Hyperbolic sine is the sine function with all of the i's missing. Okay, so that's why they call it hyperbolic sine. Okay, so that's what I just wanted to point out to you. I don't want to study this in all its detail. I don't want to talk about this. This isn't all that terribly important. I'm just showing you by analogy why they call it a hyperbolic sine. It is a sine function with all of the i's stripped away. So you can kind of consider it to be almost like the real version of a sine function. So if you haven't seen this version of what a sine really looks like, you'll get to it eventually in your math. This is the real form, the complex exponential representation of the sine function. Okay, so what I want to do now is I want to go ahead and clear the board, because that was motivation more than anything. And now I'm going to present these hyperbolic functions to you along with their derivatives, and then we're going to solve some problems. Okay, so we just already talked about the first one. The hyperbolic sine of a number is e to that number minus e to the negative x over 2. Okay, if you take a number and plug it in here, and then you will be evaluating what we call the hyperbolic sine. The hyperbolic cosine, C-O-S-H, which means hyperbolic, is a very similar function. It's e to the x plus e to the minus x over 2. And this form of the hyperbolic cosine is very similar to the exponential representation of the cosine function that you may or may not have studied, but you will definitely get to in your advanced math. Okay, the hyperbolic tangent. Okay, the hyperbolic tangent is just simply equal to the hyperbolic sine over the hyperbolic cosine, which is the same thing as we talked about before. The regular tangent function is sine over cosine, so the hyperbolic is the same thing, sine hyperbolic over cosine hyperbolic. And the hyperbolic cotangent is analogously the same way. Okay, so whereas in the regular trigonometric functions, Cotangent was cosine over sine. Hyperbolic cotangent is hyperbolic cosine over hyperbolic sine. Okay? And then the other ones fall out the same way. The hyperbolic secant, okay, is equal to 1 over the hyperbolic cosine, and the hyperbolic cosecant is 1 over the hyperbolic sine. Okay? So this pattern follows the same rainbow that I've talked about in some other sections. I mean, you've used this before. If you write them like a rainbow, sine, cosine, tangent, cotangent, secant, cosecant. And then you just put hyperbolics here at the end because these are just hyperbolics. Then it forms the same rainbow as before. Cotangent is 1 over tangent, hyperbolic. Okay. Secant is 1 over hyperbolic cosine. And cosecant hyperbolic is 1 over hyperbolic sine. So you see, once you have the sine and the cosine defined, which is what I've given you here, I've shown you what they are in terms of an actual function, then the other trig, hyperbolic trig functions are just derived from it. So really all you have to do is know these, and then all of the other ones follow the same rainbow you know, that you would have if you had the regular trig functions. Cotangent 1 over tangent, and secant 1 over cosine, etc., etc. Okay, so now what we're going to do is we're going to leave these on the board. Okay, and we're going to, at this point, talk about the derivatives of these functions. Okay, the derivatives of these functions. It turns out that they're very similar to the trig counterparts, and that's why, you know, it's so convenient to call them hyperbolic sine, hyperbolic cosine. So, for instance, the derivative with respect to x of the hyperbolic sine of x, what do you think it would equal? Well, this derivative of the sine function, the regular sine function, is cosine, and in this case it's the same thing. It's hyperbolic cosine of x. Derivative of hyperbolic sine is the hyperbolic cosine function. Okay, let's move on. The derivative with respect to x of the hyperbolic cosine function, well, what is it in regular trig terms? Derivative of cosine is negative sine. This one is pretty close. It's not exactly the same. There's no negative sign here, but beyond that it's the same. Derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is hyperbolic sine. There's no negative here like there are for the regular trig functions, but it's very similar otherwise. Derivative of the hyperbolic tangent, well, what is it? It's going to be hyperbolic secant squared x. Okay, very similar. And the derivative of the hyperbolic cotangent is going to be negative cosecant squared. Okay, so you can see these follow the same pattern as your regular trig functions. If you flip back to your Cal 1 and you start looking at the derivative of cotangent, the derivative of tangent, you'll see that it's almost exactly the same. Okay, now the derivative of secant hyperbolic, it's tangent times secant in the regular trig functions. Here it's negative secant hyperbolic times tangent hyperbolic. Okay, again, very, very similar. And the derivative of cosecant is equal to negative cosecant cotangent. Okay, so if you were to flip back and look at the derivative of the regular sine, cosine, tangent, cotangent, secant, cosecant, you would see that this table looks almost exactly the same. Derivative of tangent is secant squared. Well, here it's the same thing. Derivative of hyperbolic tangent is hyperbolic secant squared. Derivative of cotangent, cosecant squared. Same thing, going on and on and on. So everything is basically exactly the same. So that makes it easy to sort of memorize things. The only thing you need to really keep watch out for is on your test sometimes they'll have you do some problems dealing with the exponential forms of these guys. So you need to know that, and that's actually, those are very similar to the definition of the regular sine and the regular cosine, and that's why these derivatives work out so nicely. Okay, so what we're going to do is we're going to leave those on the board. That is just going to be what you find in your textbook. Okay, that's going to be what you find in your textbook, and what we're going to do now is we're going to work some problems to kind of drill it home and see how to use these things. So the first thing would be, what if, you know, in your problems or your homework or your test, it said you have a function that's the hyperbolic tangent of, not of x, of 3x. Okay, hyperbolic tangent of 3x, and you want to find the derivative of that. So what you would do is you'd say df dx, and you know that you have a tangent hyperbolic here, so you look back in your table and you see that the derivative of the tangent hyperbolic function is secant squared hyperbolic of x. But you see, the argument's different. Here I know the derivative of hyperbolic tangent of x is this, but here, I do not have that over there. I have hyperbolic of tangent of 3x. So it's really the same thing as you're taking your derivatives of your regular trig functions. You have to use the chain rule. First thing you want to do is use this rule given the argument of 3x, so it's secant hyperbolic squared of 3x, because that was the argument I was presented with. So I just use the derivative I have, but in order to make it a complete chain rule, I have to multiply by the derivative of the inside, which is just 3. Derivative of 3x is 3. So df dx is equal to 3 times the secant squared hyperbolic secant squared of 3x, and that would be how you would solve that problem to find the derivative of that function. So you see, you're doing the same thing here. You're doing the same thing as you've always done with your chain rule. You need to get good at the chain rule if you haven't already by now. It's just that here we're presented with some additional derivatives for you to put in your bag of tricks, and these will pop up in engineering and you'll have to use them, and you'll just have to know that they exist. So there's nothing magical about it. Okay, what if you had another function, hyperbolic cosine of x to the 4th power. So it's a hyperbolic cosine of x to the 4th power. Well, you do the same thing. You say, well, I have a hyperbolic cosine, so I come over here and I see what function applies. Derivative of hyperbolic cosine is simply hyperbolic sine, but my argument's different, so I have to use the chain rule. df dx is equal to hyperbolic sine of the argument I have, because this is the derivative of hyperbolic cosine, is hyperbolic sine of the argument I have times the derivative of the inside, which is 4x to the 3rd power. That's just your simple calculus 1. Derivative of x to the 4th power is 4 times x to the 3rd, using the exponent rule there. Okay, so then to finally write this answer, df dx, you just move it on to the front just for completeness, because you like to write your exponentials out in the front. So this is how you would write it on your text. 4x to the 3rd power times hyperbolic sine of x to the 4th. Okay, now let's go ahead and do another one. What if my function was f of x is equal to x squared times the secant hyperbolic of x? Okay, now here the problem is a little bit different. I know that I have this hyperbolic secant, and I know what the derivative of this is. Hyperbolic secant derivative is negative hyperbolic secant times hyperbolic tangent, so I know that, but I have x squared out in the front here, so this is a function of x multiplied by a function of x. So you have that product rule of your derivatives way back when you learned how to first take a derivative, and also that's covered in the previous course, the previous DVD. So the way you do that is you take the derivative of the first function of x times, or you say the first little function of x here times the derivative of the second plus the second times derivative of the first. If that doesn't ring a bell, you can go back and review how to take derivatives of two things that are multiplied, two functions of x that are multiplied together. So df dx is just going to be the first function, x squared, times the derivative of the second, and we already found out that the derivative of the second was this right here, so we just plug it in. Negative hyperbolic secant x times hyperbolic tangent of x. Okay? Now, it's this times the derivative of this plus this times the derivative of this. So we just write hyperbolic secant of x times the derivative of the first function, which is just 2x, because derivative of x squared is 2x. So you see, it's the first quantity times the derivative of the second, which we found from the table, plus the second quantity times the derivative of the first, which is what you have here. And now all you have to do is just sort of simplify it, and that's the answer. So df dx is just going to be 2x times the hyperbolic secant of x minus x squared times the secant hyperbolic of x times tangent hyperbolic of x. So that would be the answer. 2x times hyperbolic secant of x minus x squared secant hyperbolic of x times tangent hyperbolic of x. So you see it's very methodical. You're using the same chain rule and the same multiplication rules and everything else of doing your derivative. It's just that now you know a new function and how to take the derivative of it, and you just apply it the same way as you've always been doing. Okay, now the next problem says if you have f of t, some function of t, which is usually time, hyperbolic tangent of e to the t power. So the variable here really makes no difference at all. It's just a different one. We call it t for time. Could be x, could be whatever, but it just changes the problem up a little bit. So here you have a function within a function. You've got the hyperbolic tangent here that you know you have to deal with in the derivative. But inside, it's not just a function of t, or if you're used to thinking of x, it's not just a function of x. It's another function in here, so you have to use the chain rule. So if you look back, the function of the hyperbolic tangent was given as secant hyperbolic squared. So the first thing you do is you say, well, the derivative of tangent hyperbolic is secant hyperbolic squared of the argument that I had. So you just write it as if you just put the argument right on in there, and then in order to make a complete chain rule, you just multiply by the derivative of the inside there, and that completes the chain rule. Derivative of e to the t, you should know from your basic calculus, is just simply e to the t. The exponential function is the indestructible function. You keep taking the derivative of it over and over again, and it never dies. So you just leave it there. So df dt, just rewriting e to the t secant hyperbolic squared of e to the t. That would be the answer. E to the t hyperbolic secant squared of e to the t. Okay? Now we're going to switch gears, and those are some examples of how you would take derivatives. It's really nothing magical about it. You just apply the rules that you know from calculus, and you use these hyperbolic derivative definitions here, just as you always would, to go ahead and just apply them to the rules you know. Now we're going to switch gears and do some integrals, because you see, anytime you have a list of derivatives like this, derivative of cosine hyperbolic is sine, and vice versa, you automatically know what some integrals are. So we're going to use that, and we're going to practice that here. So what if you had the integral of the hyperbolic sine of 2x dx? So I want to take the integral of the hyperbolic sine of 2x dx. Well, you see, if you look back over at your table, you've already defined what some integrals are without really writing it. Because you know the derivative of the cosine hyperbolic function is equal to the sine hyperbolic function, then by definition, just the way integrals and derivatives work, you know that the integral of the hyperbolic sine function is the hyperbolic cosine function. Okay, you know that this is the case, because that's the definition of a derivative. So when we go back to our problem and realize it should be a hyperbolic sign here, and put that in there, of 2x, we go back to our problem and we put it as a hyperbolic of 2x, which is what it should be, then what we do is we try to use that fact, but we can't use it right away. We have to use the substitution. Okay, because we want to get this variable in here to be just a regular old variable instead of 2 times x. So what we're going to do is we're going to say u, which is our substitution variable when you do your integrals there, is equal to 2x, and then du dx is just equal to 2. Taking the derivative of this is just equal to 2. You should know that from your basic calculus. And we're going to solve this for dx because I'm going to end up plugging it in here. So solving for dx is equal to 1 over 2 du. And make sure you think that's true. You move the dx over here by multiplying, and you divide by the 2, so you're going to have 1/2 times du. And the reason we do that is the following. Because we want to go ahead and do our substitution, we say integral of hyperbolic sine, okay, of, and now we're going to use our new variable that we've defined u, because it's equal to 2x, and then we're going to go ahead and use our little differential here that we've derived because of our definition of u, and we're going to have it as 1/2 du. You see, now we have an integral in terms of u and du, and now it applies directly from the table, and that's why we did it. So we do 1/2 times the integral of the hyperbolic sine of u du. This is just your simple substitution technique you've been doing from Calculus 1. We're just applying it to here because we want to get this integral in terms of an integral in the table. And if you look back at the table, the integral of the hyperbolic sine is the hyperbolic cosine, and that's just simply because the derivative of this is this, so the integral of this must be this. That's just the way it works, because the integral is the opposite of a derivative. So you would say it's 1/2 times the hyperbolic cosine of u plus a constant. Okay, and then finally the last step is you just plug in what u was. Hyperbolic cosine of u is equal to 2x plus a constant, because anytime you do an indefinite interval, you always have to add that constant. So 1/2 cosine hyperbolic of 2x plus c. So you're doing the same techniques you did before with your integrals, your same tricks. You know, you can do integration by parts, you can do your trig substitution, you can do all of your regular substitution methods and everything else. It's just that now you have a few more things in your bag of tricks to play with, because these functions do pop up in engineering often. Okay, so what if I wanted to do the integral of the hyperbolic cotangent of x dx? Okay, the first thing that I notice right away is I'm going to go back to this table and I'm going to see if I can find something that fits. Integral of hyperbolic cotangent. Well, this one is in a hyperbolic cotangent, this one is not, this one is not, this one is not, this one is not, and this one is not. So it would seem that there's, according to what I've given you here in this lesson, there's nothing on this table that tells me what the integral of a hyperbolic cotangent is. I mean, this is the derivative of what that is, but I do not know what the integral of it is. So you're kind of stuck from the point of view of just using the table. But one of the things you need to learn in calculus is that you have to be willing to play around with things a little bit. Sometimes you have to just play around, try a few different approaches and see if it works. Go back to the beginning here and you will see that the hyperbolic cotangent is, by definition, the hyperbolic cosine over the hyperbolic sine. So let's write it that way. Hyperbolic cosine over the hyperbolic sine, okay, dx. So we've changed nothing. The only thing we've done is we've written this function as these two, which we can do. Okay, now, again, anytime you're doing integrals, you're going to have to play with things a little bit. Let's say we make the substitution that u is equal to the hyperbolic sine of x. U is equal to the hyperbolic sine of x. So then du dx, the derivative of u with respect to x, would be derivative of hyperbolic sine is, what is it? We looked in our table. Derivative of hyperbolic sine is hyperbolic cosine. So we just put hyperbolic cosine there. And now we're going to solve for dx, because I'm going to end up using that when I do my substitution. So it's going to be 1 over the hyperbolic cosine of x. I'm going to put my h's here. Hyperbolic cosine of x times du. Make sure you convince yourself of that. You move the dx over here, and then you divide by hyperbolic cosine to get dx by itself. So dx is 1 over hyperbolic cosine times du. Now let's go ahead and do our substitution and see if it makes our life easier. This is going to be equal to the integral of the hyperbolic cosine over hyperbolic sine, but that's equal to u, so I'm going to go ahead and substitute my variable, and now I have to plug in for dx, which is the definition of this differential here, dx, which arises because of our choice of our substitution here. So just go ahead and put it in. 1 over cosine hyperbolic of x times du. Now you can see right away why we did it. We did it because this cancels with this. Okay? Because of the way the derivatives are set up, when we choose it like this, we can get the numerator to cancel. So what you have is the integral of 1 over u times du, and this should be very familiar to you. You studied this in Calculus 1. Integral of 1 over x dx, or 1 over u du, same thing, is just equal to the natural log of the absolute value of u plus a constant. You always have to have your plus constant when you're doing your indefinite integrals. So it's the natural log is what the answer is. And the final step when you're doing your substitution is to always make sure and plug in what you chose. Hyperbolic sine of x plus a constant. So that's what the derivative is. The natural log of the hyperbolic sine of x plus a constant. Okay, so in this section we've introduced the topic of the hyperbolic functions. Okay, they're functions that just come about in nature, that come about in solution to engineering problems. They're not as common by a long shot as the sine and the regular trig functions, but they do come up, and so you have to know how to take the derivatives of them, and you have to know how they're defined and how they relate to one another so that you can put them in your mathematical tool bag and use them. And they're very similar in their root definition here. When you look at the exponential definition of these functions, they're very similar to how the sine and the cosine and the regular trig functions are defined in terms of complex exponentials. And if you haven't studied that yet, the fact that sine and cosine and tangent and all those are really just complex exponentials, you will definitely get to that later in your math courses. So that's why they call them the hyperbolic sine and the hyperbolic cosine, because they're so similar to their regular trigonometric functions.